Now let's go over booklet number 4. The main topic of booklet number 4 is conservation of energy. When we talk about conservation of energy, we start our conversation with mechanical energy. What is mechanical energy? Mechanical energy is the sum of potential and kinetic energy. So let's write it down. Mechanical energy is the sum of potential and kinetic energy. When we talk about potential energy, we talk about height. Okay, the main aspect of potential energy is height. So if you do not have height, you do not have potential energy. That's what basically potential energy tells us. Okay, if you have height, then you have lots of potential energy. So then what should be the equation? The equation of potential energy is mgh, and kinetic energy is half mv square. So potential energy, m is kilogram, g is meter per second square, and h is meter. So kilogram meter square over second square, and there is a and we call it joule, and it is a scalar quantity. On the other hand, kinetic energy is mass is kilogram meter square over second square. So kilogram meter square over second square, and that is joule, and it's a scalar quantity. In fact, all type of energy is scalar quantity. Even E equal mc square, all type of energy is scalar quantity. So when we talk about energy, we are talking about scalar quantity. Okay, so I think this was the motivation to solve the do now problem. So do now problem, a man dropping a rock from 10 meter above the ground. The rock is 100 kilogram. We want to find the mechanical energy. We want to remind ourselves that mechanical energy throughout location A, location B, location C would be constant. So at location A, we know maximum potential energy, and location C, maximum kinetic energy. In the middle, there would be half and half. So this is what we expect to get. So now let's do the math. Location A, potential energy is mgh. So potential energy is m is 100, g is 10, and height is 10. So potential energy on the top is 10,000 joule. Now we're going to find kinetic energy. Kinetic energy on the top is 0, is because velocity is 0. So we're going to calculate the mechanical energy. Mechanical energy, potential energy plus kinetic energy. So mechanical energy is 10,000 joule. Now at location B, now we're going to do location B. Potential energy would be 50% because it's in the middle, 5 meter above the ground. So we don't have to do the math. We can use conservation of energy to hypothesize that potential energy and kinetic energy would be 50-50 because is in the middle of the trip. So potential energy is 5,000 joule, kinetic energy is 5,000 joule. So total mechanical energy is 10,000 joule. 10,000 joule. Okay, now at location C, potential energy would be 0. Kinetic energy, all the potential energy transferred to kinetic energy. So kinetic energy should be 10,000. So mechanical energy again remains same. Mechanical energy is 10,000. So what do we know? We know that in a closed system, mechanical energy is constant. In a closed system like this, mechanical energy is conserved. It's constant. It can transfer from one form to another form, from potential to kinetic, kinetic to potential. Okay, now let's check problem number 2, and that is the big challenge. All right, so here's what we want to find. We want to find the velocity at the equilibrium. So what is the velocity at the equilibrium? So let's draw the equilibrium. Equilibrium is a point where the height from the bob to the ground is 0. So if you draw a ground, the height from the bob is 0, and there is other reason this is equilibrium, because the net force acting at that location is 0. Now what is height? This is the height. Okay, the green minus this dark is gonna be equal to height. Okay, this is our goal. Now how can we find this dark one? Well, it's so simple. It's by trigonometry. So this is 55. All right, so what are we going to do now? We're going to write cosine. We can use ka. So cosine 55 degree is equal to Jason, and Jason is, let's call it x over hypotenuse, which is I believe this is 2. This is given. This is 2. So now x is 2 cosine 55 degree. So 2 cosine 55 degree is how much? Cosine 55 times 2 is 1.147. So x is 1.147. So x is 1.147. So x is 1.147. Okay, that's x. So now we know our x, so I can write x 1.147. I know the other one as well. Other one is 2. So now I should be able to find height. Height would be 0.85. So height is 0.85. So height, finally we know height is 0.85. okay, all right, so we know height. We should be able to now find the velocity at the equilibrium. So how can we do that? So, well, velocity, there are two approaches. We can find the potential energy over here, and then let's show you both ways. First, we're going to find the potential energy right here. Potential energy right here is mgh. So that means the mass is, the mass of the object is, I believe, I don't remember. Let's see. If I don't remember, I'm not going to use it. I'm just going to use potential energy on the top is equal to kinetic energy on the bottom. So mgh is equal to half mv squared. cancel. So v is 2gh, and that's as simple as that. Velocity is, you don't need mass. If you don't have mass, don't worry, you don't need it. G is 9.8 and h is, we found it, 80.85. So velocity is 2 times 9.8 times 0.85, and that would be 16.66, and the square root of that is 4.08. So velocity is 4.08 meter per second right here. This is the velocity. Now we're going to do the final problem, and that is next problem. Let's do the next problem.
At my chin, and I cannot move any further back, so there's no cheat here. I'm going to release it right from my chin here. You realize, as you have just seen, that the slightest push, and this will be my last lecture, and no book signing afterwards. And I have to tell you something. I couldn't sleep all night. I don't want to see it. And I'm going to count down from 3 to 0. 3, 2, 1, 0.
This video we're going to prove will the bob kill Mr. Berry, and this is how we're going to do it. We're going to draw a normal line. On the other side, we're going to draw the bob, the same bob we have left. We have the same bob, right? We want to prove that theta initial is equal to theta final. If we can prove that theta initial equal to theta final, then the bob will oscillate back and forth, and never go further and hit his chin and kill him. This is the idea. If the theta initial is not equal to theta final, then the story would be different. So we're gonna set theta initial equal to theta final, and we want to give a proof, and that is mgh initial is equal to mgh final, is because over here you have maximum mgh and over here you also have maximum mgh, is because this one is changing the direction, making the velocity 0. This one also changing the direction, making the velocity 0. M is 100 kilogram for this side and 100 kilogram for that side. M is constant, you can cancel that. Acceleration due to gravity is also constant. So H initial is equal to H final. So when we talk about H initial, what do we talk about? We talk about L minus L cosine theta initial equal to L minus L cosine theta final. What do I mean? I mean I have a right angle triangle, and then so this is Bob, this is L, this is Bob, this is actually H, this is L minus cosine theta, L cosine theta. Okay, so L minus L cosine theta is actually H. So that's basically what it is. Okay, so you can cancel L and L, you can cancel, so negative L cosine theta initial equal to negative L cosine theta final. You can cancel this and this, so you have cosine theta initial equal to cosine theta final. Cosine cancel, so theta initial is equal to theta final, and we just proved that theta initial theta final. So Bob will never go further, hit Mr. Barry's chin to kill him. So Bob will exactly stop right here before his chin, is because of conservation of energy, because theta